Okay, last time uh, we we were talking about how to manage the memory. We said that of course memory is a resource, an operating system has to manage it, and it should allocate enough space for each process, and it should provide protection between the processes. And with the introduction of the address space concept, abstraction, each process should be able to run like they have their own memory without caring much about the other processes. That's what we said. And then we talked about managing the memory, managing the free memory for the operating system. We said that there are two ways of doing it. One is the bitmap memory, and the second one is the linked list. Okay, so
So you can't see your slide.
you cannot see my slides,
Yes,
but I am. What are you seeing?
Microsoft Teams.
I don't understand. It shows that I am. Okay, I share it again then.
Yes, now we can see.
Okay, it looks like I shared the wrong window. So two ways of managing the memory, free memory. One is the bitmap version. The second one is the linked list. Bitmap version keeps a single bit for each block of the memory. You divide your memory into blocks. Okay, usually you will say that my memory blocks would be 2 to the power 2 to the power 12 maybe. Okay, so 4k blocks in my memory, and each block is represented by a bit. So if the bit corresponding to that block is 1, that means that some process is using that memory. If it is 0, then nobody is using that memory. That memory is free to use. This is the bitmap representation of the memory, and this is the linked list representation of the memory. With the linked list approach, with the linked list approach, what you do is you say that starting from block number 0 for a length of 5 blocks, it is occupied. There is a process. Okay, this is my first node, and following the next node pointer, I come to the second node. Second node says that starting from block number 5, which is this one, block number 5, for a length of 3, which is this length. Okay, so this is 3 length, block number 5. Okay, and there is a hold, so this memory is available. So when the operating system gets a new request that says, a process says, I need 3 blocks of memory, this space is good enough for that. Okay, and you can see it from this linked list representation or the bitmap representation. Okay, which one is better? Again, like always, it depends. Since we are talking about them, since we are giving the algorithm, we wouldn't give you an algorithm that is not useful. So it depends. If you don't have many processes in your memory, if you have only a few processes, then this linked list approach makes sense. Why? Because you will have to keep only a few nodes, 4 or 5 nodes, and that's it, right? That would be very, very flexible. But if you have many processes, many occupied memory block lengths and whole lengths, then in that case you would have lots of linked list nodes, and that will be difficult to traverse and find what you need, and etc. In that case, maybe a bitmap version would be more efficient because the size of the bitmap table is fixed. Okay, size of the bitmap table is fixed. So what is the size? Size is your memory size over 2 to the power 12. Okay, and this is the number of bits that you will need to store this table. Okay, so um, bitmaps, memory is divided into small allocation units. Size of the allocation unit is a design issue. Okay, what should be my block size? It should be like 4 kilobytes, 5 kilobytes. Okay, so maybe I should ask you this question. What is the trade-off? I mean, should I make this 2 to the power 10 bytes for block, or should I make this 2 to the power 20? How do I make this selection? What is the trade-off? Obviously, I mean, smaller numbers are bad, larger numbers are bad too, okay? So what is the problem with the smaller numbers? If I keep my block size here, each block, let's say, if each block is 1 kilobyte, if each block is 1 kilobyte, or if I should make each block should be maybe 1 megabyte. Okay, so what is bad about 1 megabyte? If I make each block 1 megabyte, what would be the problem?
So we allocate pages to, I guess, one process only. So if the process doesn't use the whole page, it would be wasted.
Yes, exactly, like Emek said, but we wouldn't call these pages. These are memory blocks, okay? Pages are very different and we are going to see them, okay? These are memory block. If I allocate, let's say, if there is a process, that process needs 16 kilobytes of memory space, that's it. 16 kilobytes of memory space. The minimum that I can allocate is 1 megabyte, right? Because each bit here represents a 1 megabyte of memory. So what does that mean? That means that the rest of this memory, this one block, will be wasted. Okay? It will be wasted. So that's not good. What is the positive side? What is good about larger block size?
The table size is small.
Yeah, table size is going to be very small, right? Table size is going to be very small because since I am using a single bit to represent a 1 megabyte of memory block, it will be very small for this page table. Also, it will be small for this. Well, maybe it is not for this one, right? Because keep I am going to keep one node for each process. Yeah, and in that case, maybe it is not a very, of course, it is still advantage, but it is not a very big advantage for this one, but it's a big advantage for the bitmap. So the trade-off is this: if you if you keep your block sizes small, your page table, your bitmap table will be large. Okay, that's not good, but your wasted space will be small. Okay, but if you keep it large, if you keep your block size large, then this table will be small, but you are going to waste lots of memory space. The place that you don't use, for example, this process A, of course, you are not going to use some part of this, the last block, right? The part that you don't use in your block is called, okay, this problem is called internal internal fragmentation. Okay, that's called internal fragmentation. Okay, good. So as we said, it's a trade-off. Okay. Also, searching for K allocation unit is expensive. You have to look it up. You have to scan your whole table and you have to find the appropriate block. Okay, while we are talking about this searching for K allocation units, maybe we should look at some of the cases with the bitmaps and the linked lists when they are doing allocation and deallocation. For example, if I am using the linked list, okay, giving back the memory inside the bitmap is no problem. What you do is, let's say I like to give back this 1 2 3 4 blocks. Okay, all I do is I come here and I just switch them to zeros. That's it. That's what I do. Okay, so it is as simple as making them zero, and that's it. The important thing is finding that and finding the available blocks and etc. But for the linked list approach, this is what you need to do. Okay, if X terminates, you go there and of course there should be a node for A, node for X, and node for B. Okay, if X terminates, my linked list becomes a node for A, and node for H, a whole, and node for B. That's it. Okay. Here, if X terminates here, then I need to merge these two. Remember, I have this place now. Okay, this used to be the X. I need to merge these two into a single whole. Okay, if I do that, I need to merge these two. But if I do this, I need to merge these three into a single whole. So memory management with linked list requires, okay, merging some nodes after the deletion. We don't have this problem with the bitmap version. Okay, good. Any questions so far? Okay, if there are no questions, I am going to look at these algorithms. Um, the algorithms are for memory management algorithms. So if the problem is this, let's say I have a new process K, and this K needs 2 blocks of memory. Okay, which block should I choose? Should I choose this block or this block or this block? Okay, should I choose this one or this one or this one? What is my algorithm to choose between those two? Okay, and as the names show, okay, we look at the sizes, we compare the sizes. I need 2 blocks. Okay, and I am going to find these 2 blocks using these algorithms: first fit, next fit, best fit, worst fit, and quick fit. Okay, let's look at the first fit. As the name implies, first fit, okay, you just check your list until a large enough block is found. As soon as you find a block that is large enough, you say that, okay, I am going to allocate as much of it as is needed. Okay, in that case, if I am doing this 2 block, and if this is my case, I need a 2 block. I look at this, this is a P, this is a whole. This whole says that 3 blocks available. I need 2 blocks, so the first fit says that, okay, this is good enough, so I pick this one. So after I pick this one, I said that, okay, this is going to be, okay, take this out, and a new, okay, P5 2 and H7 1, and then I would connect here this one. Okay, so that's it. So this is the first fit approach, first fit algorithm to find the memory positions. Find the first available and allocate as much of it as needed, and return the rest to the free list. Okay. When you are freeing memory, okay, this is allocation. When you are freeing memory, of course you must merge the adjacent blocks. Okay, so how do you do that? In that case, if you are merging the adjacent block, then obvious answer is we order the linked list by addresses like I did here, Okay, so this linked list is linked is uh, ordered with respect to the address. Okay, so it is 0, 5, 8, 14, 18, 20. It goes like that. So what is the alternative for the ordering for this linked list? So in this case, I ordered it using the address of the block. What is the alternative?
Size maybe.
Yeah, size might be another alternative. I mean, if I if I if I order these lists with respect to size, it would be very easy to find the first fit, right? What is the solution? The first node, right? Because the first node is the largest one, then always I am going to take it. Okay, but if I do it with the size of the block, then the remaining part has to be inserted to the back to the list again. But in that case, I need to in that case um, I need to go back and scan my list and insert the remaining parts of that available block. Okay. Give an example. Okay, good. So this is the first fit algorithm, and as the name says, the next fit says that next fit says that don't start your search from the beginning all the time. Okay, for it's just a small modification for the first fit. Wherever you have left in your last search, start from there. Okay, the next search start from the results of previous search. Okay, let's say this is my linked list. I made a search. And I found that this is my hole. I allocated it. I did all my bookkeeping stuff. Next time when I make a search, I don't start from the beginning, but I start from this point. That's called the next fit. So you don't keep scanning from the beginning all the time. Okay? So this is a small modification to first fit algorithm. And then people say that first fit seems wasteful. Why? Because it finds the first large enough block, okay, sequence of block, and it allocates it. So if I need 2 kilobytes of space, and if there is a hole, that is maybe um, that is maybe 3 kilobytes, or maybe no, let's make it larger. So that's maybe 20 kilobytes. I am going to divide it into 2 kilobytes and 18 kilobytes. Okay, I am assuming that my block sizes are 1 kilobyte. Okay, so I keep making this smaller, and maybe I need the space for larger processes. If a new process needed 20 kilobytes of space, then I don't have that space anymore. Okay, so they say that instead of doing the first fit, let's do the best fit. So in this case, I am going to scan the whole linked list or whole bitmap table, and I am going to find the preferably the exact fit if it is available. Otherwise, I am going to find the smallest hole that can hold this 2 kilobytes of data. So if 2 kilobytes hole is available, I am going to use it. Otherwise, 3 is good, 4 is good, 5 is good, whatever. Okay. So of course, for the best fit, the better solution would be order the linked list by size. Okay. I order my linked list by size. In that case, finding the best fit would be easy. Of course, I cannot do anything about the ordering with the bitmap approach. Okay, with the bitmap approach, ordering is fixed. I cannot do anything, and ordering is, of course, ordering is of course by the address. Okay, so with the best fit, if I keep my order with respect to size, finding it easy, but making the merging and making the modification is less efficient. Why? Because I need to find the appropriate position for the remaining part of the block. Okay, and people have realized that best fit isn't more efficient than the first fit. What was the problem with the first fit? First fit says that if you have 20 kilobytes of block and if you need 2 kilobytes, I'm going to divide it into 2 because I found it is the first fit. Best fit said that no, try to find a block, maybe a 3 kilobytes of block. This is 3 kilobytes. I will take this part and this part will be available. 1 kilobyte will be available. Okay, but they say that this is not more efficient in terms of memory usage. In terms of memory usage, okay. Sometimes it causes more wasted memory. Why? Why do you think so? Why do you think best fit?
Maybe there will be lots of small free spaces, but the processes will not fit there.
Exactly, Galip. Because most probably the remaining parts of these flow blocks will be very, very small memory chunks, like 1 kilobytes, 2 kilobytes, 5 kilobytes, whatever. No process will want that much small space. So you will end up in your memory will be like lots of processes here and small memory there. Lots of processes, a small memory. Lots of processes and small memory. So your holes will be like this. If you add them up, you have lots of space, but since they are like far apart from each other, then what we are saying here is that this is not good. Okay, this is causing loss of memory inefficiency. This is called external fragmentation.
Sure.
Fragmentation. Okay, and this is not good either. Yes, do you have a
Talking
question?
about processes, yes, I do have a question. You're talking about processes here, but I remember that a similar thing happens while saving stuff to the disk hard disk or SSD. Uh, is it true that these are similar or completely different ways of thinking while slicing the spaces?
Well, yeah, well, sure. As long as you are doing some allocation from a huge resource, either it is a memory or the hard disk space or some space that is on some other device, you have to do this kind of stuff. So you will see these kind of problems: internal fragmentation, external fragmentation, with this kind of allocation, space management problems. And we are going to see we have exact problems with the hard disks too, because you need to allocate hard disks too.
Thank you.
Okay, and since you asked it, this bitmap version, okay, this bitmap version of allocating the disk space is called file access table or FAT. Okay, I'm sure you heard about FAT 16, FAT 32, right? Okay, so this it might be called differently, but again, this is a resource, a large resource, and we are allocating parts of that resource to processes, and I need to keep track of what is available and what is not available. Okay, and again, we are talking about the memory blocks here, and when it comes to disks or SSD, whatever the secondary storage, we will be talking about the block sizes there too. Okay, good. So we talked about this best fit, and then why don't we try just the opposite of the idea of the best fit, worst fit? Okay, I am going to find largest block that I can allocate. Okay, that's not going to cause any external fragmentation, right? Best fit causes lots of external fragmentation because you end up producing lots of small holes. Worst fit is not going to um, is not going to cause such a problem. Okay, leaves useless blocks. Okay, how about the worst fit? Pick the largest block and subdivide it. Okay, and it turns out that this idea is not very good. First fit and best fit are better and are pretty close. Okay, and so how do they calculate this? How do they know that which one is better than the other one? There are no theoretical solutions for this. Okay, all you do is you run simulation. Okay, you run simulations. How do you run simulations? You will say that, okay, like your homework. This is my simulated MIPS processor. This is my operating system. I am simulating it, and this is the memory allocation algorithm. Okay, this is the memory allocation algorithm that I am going to use, and you compare the fragmentation of your memory. You compare the amount you spend for searching for the blocks and etc. And so for first fit, as much as 1/3 of the memory may be unusable, they say. Okay, so that's very inefficient, right? And we are talking about the first fit is a better versions of these algorithms. 1/3 of the memory may be unusable. So what do you do? I mean, if you end up doing this, okay, if you end up doing this as fragmentation, small fragmentation there, and you know that if I add these small blocks, it might be equal to 1/3 of my memory. That's very large chunk of my memory, but since they are not contiguous, I cannot use them. So what do I do? If this is my process A, B, C, and D, what do? I would do this compaction process. Compaction. Compaction is this. Compaction is this. You will say that, okay, this is my whole memory. I will move, A will stay here. B is going to be will be moved here like B. C is large, C will move here, and D is going to move there, okay? So rest of it will be free now. So I can start using this large chunk of memory. But compaction, what is the problem with compaction? The operating system needs CPU time, and all of these processes has to be suspended because they cannot run while their memory is being moved. Okay, so um, you need to have one way of being able to moving your processes from one position to another position in your memory. Okay, so that's called compaction. Compaction is a solution for external fragmentation. Okay, can you suggest me a solution for internal fragmentation? I introduced this compaction idea for external fragmentation. It gets rid of these small holes, it makes them large. How
I
about
have
the
a
internal
question.
fragmentation? Yes, Beyza.
I missed the difference between external fragmentation and internal fragmentation. Can you explain it again?
External fragmentation is the small holes that you cannot use because these are each one is a 1 or 2 kilobytes of hole, free space. But I cannot fit a process in there, right? Because processes need larger spaces. These are called external fragmentation. Internal fragmentation is this. Let's say this is 8 kilobytes of space, 8 kilobytes of space assigned for process A. But process A needs only 7.5 kilobytes of space. That means that some part inside process A, half a kilobyte, will not be used by process A. Okay, this has to be that way. Why? Because the process A has to occupy 8 blocks, memory blocks. Okay, so the last part of that memory block will not be used by A because A needs 7.5 kilobytes of space. And at the end of each process, you will have these kind of uh, unusable spaces. That's called internal fragmentation.
Okay, thank you.
So internal fragmentation is the memory that cannot be used inside the address space of each process. External fragmentation is empty space, but operating system cannot allocate it to any process because they are too small.
Sir, is there's a solution for this? Can you start the other process, the some different process, where the first process ends with the internal fragmentation, like point 5 kilobytes of space like that?
Are you talking about some kind of an overlap, like place process K here, like that?
Yes.
Well, in that case, the address spaces of A and K will be overlapping, and that's not good in terms of protection. And I cannot do that anyway because my addresses, my memory positions can start from the beginning of the memory blocks, and they have to they have to align with the memory block borders, right? So I cannot start in the middle of a memory block. It has to be from the beginning because my bitmap table is like that. My linked list table is like that.
So don't we use for internal fragmentation, we use heap and stack in processes, right?
Yes.
So
So you are saying
if
that
in
these processes need extra space anyway.
yes,
Yeah. So it is like what Ebru says is this. What Ebru says is this. Um, our processes are like this anyway. Okay. This is my process structure. Let's say this is 8 kilobytes of memory allocation. Oh, sorry. This is 8 kilobytes of memory allocation, and I will need some extra space inside my process memory anyway because my heap is growing upwards, my stack is growing downwards. So why should it matter? I mean, I will keep that extra space inside my room for growth, and that would be a solution. But still, again, I mean, if process B says that I need 8.5 kilobytes of space, you have to assign, if the process B says that I need 7.5 kilobytes of space, okay, including my room for growth, you have to assign at least 8 kilobytes. Yeah, that's a good way of looking at it, but again, you cannot be precise. You cannot be precise. Well, okay, I'm not going to talk much about these best fits, first fit, worst fit, etc., because we will come up with an algorithm that doesn't use any of these actually. It doesn't make any sense for that algorithm. That algorithm, and is the most commonly used one, is going to solve all of these problems. You don't need any compaction. You will not see any external fragmentation, no external fragmentation at all. But the internal fragmentation will be there. That's you cannot avoid the internal fragmentation. But effect of it will be minimized. Okay. Okay. Some people say that a little bit better implementation. Remember our linked list. Remember our linked list solution. It was the linked list solution like that. Let's say I have for say process from 0 to 7. It's a whole from 8 to 8, and then a process from I don't know 15 5, and then 20 is a whole from 20 to 5. Okay, good. So this is what I have. They say that since in my memory I know that this space is empty and this space is empty, I know that. Okay, where do I keep this linked list? Okay, I will keep this linked list. I will keep this linked list in my memory, my kernel memory. Okay, so let me divide this into two. First is the process 0 7, and then process 15 5, and these are the processes, and these are the whole 8 and 8, and then whole 20 and 5. They say that keep this list, okay, keep this list in the free memory. Okay, keep this list not in the kernel memory but in the free memory, because nobody is using the free memory. And if you keep this list in the free memory, this list will get smaller and smaller if there is no free memory. But if there is free memory, then that memory is usable, right? So operating system can use that free memory to do some useful things. Okay, you cannot say that I don't have any free memory. If you don't have any free memory, then this linked list will be very small, or no linked list in there. Okay, so this is automatically adjust itself. So whole list can directly use the free memory, a better implementation. Okay, good. Okay, so these are the algorithms that we use for allocating space for available for the processes. And when we do the deallocation, of course we have to do the bookkeeping. We have to merge the nearby nodes with the linked list implementation. Still, we did not solve the problem of, let's say, this is my whole memory, this is my OS. Okay, I have a process A and I have a process B. I don't have any space for process C now. I need to swap out this A, okay, and I will put C in here. Again, this part is empty and this part. So I need to do lots of swapping in and out, okay, and I don't like it much, even though some part of the program B is not used at all. Okay, I mean B doesn't use the whole memory. It needs the whole memory, but it doesn't use the whole memory all the time. It needs only a small part of it. Later it may need the other parts of it. So people came up with this idea of overlays in 1960s. They say that a programmer, when they write their programs, they say that, okay, this is my program. This is my program A. I am going to do it this way. Okay. I will divide my program memory into three parts. Okay. Overlay 1, overlay 2, and overlay 3. Inside this overlay 1, I will have my function 1, function 2, function 3, and all the data structures related to it. Overlay 2, I will have function 5, function 6, and related data structures. And in O3, I will have function 8 and function 9 and related data structures. And I know that if I am using F1, F3, F2, I don't need these or I don't need these. If I am using F5 and F6, I only need these two and the related data structure. So that would be the part of the design for a programmer. The programmer makes this decision. And each part is called an overlay. Okay? And the programmer tells the operating system that load my overlay 1 or load my overlay 2, or he would say to the operating system that I don't need the overlay 1 anymore, overlay 2 anymore. Okay? In that case, you are always in the memory of the operating system, but not the whole memory of process A is loaded at the same time. Okay? You are loading only a small part of it, 1/3 of it. The rest stays on the desk. Okay? So the rest kept on the desk, swapped in and out of the memory by the program itself. So the program is doing the memory management up to a point. Okay, these are called overlays. This is nice. Why? Because now you can have a system, operating system. Okay, A, B, C, and D, and each one is occupying only the 1/3 of their required memories in the memory because they are all overlaid. Okay, because they have all their overlays, and the overlays are managed by their processes, not by the operating system, but their processes. So what is the problem with this approach? It looks nice, but there is a problem with it. What is the problem?
Is it too slow because they're on the disk?
Well, swapping is always going to be slow. I mean, if you need to fit A, B, C, D in your memory, you will have to take the hit. You will have to take the hit of swapping. Otherwise, what is the alternative? The alternative is OS here, and A needs large amount of space, and C needs this one. There is no space for B and D. So to load B, you need to swap out the whole A and put B in there, right? So that's the alternative. The alternative is needs more swapping. No, that's not it. So what is the problem with the overlays? This is the problem. Tell me the problem.
Now we have to swap our program constantly. Isn't that also lots of swap?
Yeah, but as I said, yes, swapping is a problem, but there is no escape from swapping. Swapping is going to happen. And if you are the programmer, if you are smart, maybe for the whole execution of your program, you are going to swap O1, O2, and O3 only once. Think about a game program, a game process. Okay, let's say it's an arcade game. You need to load lots of data from the disk because arcade needs lots of environment data. Okay, so at the start of the game you need to load your environment, but when your character starts moving, okay, sequential of course you are going, so whenever you move to a new environment, you need to load the data for the new environment, so another overlay. Okay, so usually you don't go back and forth between two environments, so overlays work fine. The problem is with the programmers. The programmers has to do their own memory management, and that's confusing and that's difficult for the programmers. Okay, you have to say that I need these functions in my memory for this part of the program, and I need my functions, these functions and classes and the data for this part of the program, etc. And that should be part of your programming design. Okay, software design. That's difficult and that's kind of error prone. That's not good. We don't like it. That's called overlays. Okay, good. Any other questions? If there are no questions, I will start this idea of virtual memory. Up to now, whatever I told you, they were the solutions for 1960s, maybe at the end of 1950s, maybe. And maybe these are the solutions for the very early personal computers, etc. We don't use them much now. Instead, we use this idea of virtual memory. Okay, with the virtual memory, okay, we don't have this allocation inefficiency anymore, like the problems with the worst fit, best fit, etc. You remember those? We don't have external fragmentation. We need to do compaction. We don't need to do compaction. Relocation is not a problem. We are not going to do relocation, and memory protection becomes very easy, and many other advantages. Many other advantages, and the overlay becomes automatic, and these all will come with this virtual memory and pages. And after the break, we will continue with this idea of virtual memory, which is very simple idea, but we need help from the hardware and operating system. Okay. Okay, so 10 minutes of break. Let's be here around 11:34. Okay, virtual memory. With the virtual memory, each process has their own address space, and they don't have to do anything like the overlays. They don't know anything happening under the hood. All they do is they just use their regular addressing to access the memory and whatever they want. It is the job of the hardware to convert the addresses used by each process into a different address. Okay, the processes use their own addresses, but we call them virtual memory addresses because those are not physical addresses. Those addresses are automatically converted to physical addresses with the help of the hardware. Okay, maybe this figure will explain it a little bit more. So the CPU is running code. This code accesses the memory addresses. This code accesses the memory addresses, and when the CPU produces those addresses, this memory management unit takes those addresses and converts them into physical addresses. The CPU thinks that it is using a virtual address, okay, but all of those addresses are converted to the physical addresses that can be used to access the memory. Okay, so all of our processes running their instructions in the CPU, they think that they own the CPU, the whole CPU, which is not true because they are sharing the CPU with other processes. Also, they think that their addresses run from zero address 0 to some high number, maybe 4 megabytes. Okay, but all of their addresses are automatically converted to physical addresses that is good for the physical memory. Okay, so this is called virtual memory, and we do this technique with the helping of paging, and this picture is the main picture actually. So each process thinks that they have 64 kilobytes of data. Okay, 64 kilobytes of address space. This is called virtual address space. So I can say that access address number 0000, which would be this one, or I would say access address number 60,712. Okay, so anything between 00 to 64K is okay for the processes. The process thinks that all the addresses are valid for itself. But in reality, this is what I do. This is what the operating system and the hardware does. We divide this virtual address space into pages. These are called pages. Okay, if each page is 4 kilobytes, okay, each of them are 4 kilobytes, then that means that 64 over 4 is there are there are 16 pages. Okay, 16 virtual pages. Okay, the program doesn't know that it is divided into 16 virtual pages, but operating system and the hardware does. Okay, they do. So there are 16 virtual pages, and the operating system keeps this table. This table says that if if your virtual address is within between 0K to 4K, okay, if your virtual address is from 0K to 4K, let's say I am trying to access the address number 2000, so it is in this range. So this table says that your physical address is actually in the physical memory, and as you see, my physical memory is only 32 kilobytes. It is half my virtual address. Okay, so my process thinks that it has total of 64 kilobytes available, but my physical memory can hold at most 32 kilobytes of data. It is half the size, but the process doesn't know anything about it. When the process tries to access this address number 2000. Okay, it should be in the first page, but in physical memory it is actually in the 0, 1 to 2, page number 2. Okay, it is in the page number 2. Okay, when I when I when I try to access this address space, okay, I am using a memory location somewhere here in the 0, 1 second physical page. Okay, those are called page frames. Okay, there is this translation going on all the time. Whenever I try to reach a memory location as a process, okay, the computer hardware translates my virtual address into physical address all the time. So if I am trying to access an address inside this page, I am using this page here. If I am trying to access a memory page in this page, a memory address in this page, I am using somewhere there. Okay. So what happens if I try to access somewhere here, like 29,000 something? What happens if I try to access this one? Let's say I like to write to address 29,000 some value. What happens?
So segmentation fault will occur if it's not allocated for us.
What is segmentation? I never talk about anything like segmentation.
From disk.
Beyza, say it again.
It's to be loaded from disk.
Well, yeah, exactly. This part of the memory is not available. Okay, this part of the virtual memory, well, it is available, but when the hardware and the operating system tries to find a page, okay, a page frame inside my physical memory, it is not available. So what am I gonna do? Of course, I will ask the operating system to load this page from the disk and swap one page from this physical memory. Let's say maybe this one. I swapped it out. Now this is available, and then I am going to put this arrow here to there. So okay. So what I do is I did a page replacement. And this process, I mean this process happened, the loading the page and making it available to the program. Okay, it's called page replacement, but my program doesn't know anything about it. My program thinks that it accessed this address number 29,000. My program doesn't know that this page replacement has occurred. It doesn't know. Okay, that's why it is called virtual. And that's why we say that our programs don't know that they are not using the physical memory. They use their own virtual memory, and virtual memory is something nice. It starts from 0, it ends with 64K, and I can do anything that I want with my virtual memory. And what is happening actually, every time I make a memory reference, reading, writing, modifying, whatever, all of those addresses that I produce, that I use, will be translated to this structure. And if the data is not available in my main memory, it has to be loaded from the disk. Okay, if the data is not available on the main memory, that's called it's a page fault. Page fault. Okay, what MX said in a few minutes ago, segmentation fault, segmentation error, whatever. No, it is not. Okay, we did not talk about the segmentations yet. Okay, so page faults are inefficient in terms of memory access, but when it happens, the operating system handles it with the help of the hardware. and our processes don't know anything about it. It's like process switch. Okay, when the process switch happens, our processes don't know about it, right? They don't know. Okay, we think that I execute an instruction and instruction just executed, but in fact maybe the process has switched. Maybe I was suspended for a few microseconds, milliseconds. I have waited. I was in the block queue and then maybe in the ready queue. I don't know anything about it. It's same thing here. Okay, same thing here. All I know is that I have this nice virtual address space and I'm using it. So let's look at how this translation is done. It looks like it is expensive, but with the help of the hardware, it is not that much. Okay, it is not that much because the hardware is going to help us. This memory management unit is going to help us in translating those virtual addresses into physical addresses. Okay, let's look at that. Okay, so these are some definitions. Each program has its own address space, and this address space is broken into chunks called pages. Pages are usually 4 kilobytes, although it says system dependent, and it is system dependent and the configuration dependent. For Windows, your pages could be half a kilobyte, 1 kilobyte, 2, 4, 8, and it goes on like that, and it changes. Okay, your program generated addresses are called virtual addresses. Okay, those are the virtual addresses, and they form the virtual address space. Whatever you produce, whatever you have in your assembly code, they are all virtual addresses. They are not physical addresses. They are not physical addresses. One of the nice things about this picture is, if I, let's say, if I move this page from this location, let's say, to this location, all I need to do is I draw a new arrow like that. That's it. Okay, and as you see, my virtual address space is contiguous. Okay, it starts from 0 and it nicely increases up to 64K, but in my physical memory nothing is contiguous. I can put any page at any position that I like. So that means that there is no external fragmentation. Why not? I don't have it because I don't have any position dependent addresses anymore in terms of virtual addresses. Okay, so I put all of my allocation units are 4 kilobytes. If I need to allocate 5 page frames, they don't have to be contiguous. They can come from different parts of the memory. Okay, I will put all that information into my translation structure. Okay, good. So pages, we talked about it. Virtual addresses and virtual address space, we talked about it. Okay, so virtual address space consists of fixed size units called pages. Okay, these are the pages again. The corresponding unit in the physical memory are called page frames. These are pages, virtual pages. These are physical page frames. Okay, for each page in virtual memory, for each virtual page, there should be a corresponding page frame. If there is no corresponding page frame, and if we try to access a memory location at this position, okay, we call this a page fault. And page faults are expensive. Page faults are expensive. Why? We need to load some data from the disk. Remember, this looks like very similar to swapping or overlays, but everything is done by the operating system automatically. And with the swapping, remember, sometimes we had to do the compaction, moving the processes around. In this case, I don't have to do any processes, any swapping. I don't have to do any swapping explicitly as a programmer, and there is no problem of compaction. there is no problem of relocation and etc. Of course, this translation is important. Let's see an example of this translation. Okay, this is one example. Okay, this is let's say our MMU, memory management unit. This MMU takes the virtual address from this end. I take the virtual addresses. Okay, from this end I produce the physical addresses. Okay, so I take the virtual addresses and I produce the physical addresses. And this is one example here. It says that incoming virtual address is 8196. Okay, 8196. Is this okay? So let me see if I am. Yeah, this is going to be 6. Yep. So this is the same as that one. So what I am going to do is 8000. What was it? What is it again? 8000. 8196. I will get it. So it is inside this page, virtual page. So in physical memory, it has to be in this page. Okay, but I need to find the exact memory location so that I can produce it. This is what I am going to do. This is what I am going to do. I since my pages are 4 kilobytes, I take this last 12 bits of this virtual address as an offset. This is called offset. I am not going to change it. Okay, this is called offset. This part of the um, this part of the address, virtual address, is not going to be changed. The remaining part, okay, this 4-bit part, is going to be used as an index into this page table. Okay, this is a page table. This page table has 16 elements, and each element gives me the corresponding physical page frame of that virtual page. So my virtual page in this case is 0010. I look at this one. 0010 is this. It is 2, right? I look at this one. 2 says that my physical frame is 110. 110 is 6, right? 6. So that means that I am going to produce 110. So this is what I do. I take this offset exactly. This offset is same as here. Okay, this is exactly same as that one, that offset as the arrows here, right? I take it and then I replace this virtual page frame number, this 0010, with this 110. Okay, now this one becomes my my physical frame number. So in effect what I did was I converted this green box into red box and I kept the rest of the address the same. So I am converting the first 4 bits of my virtual address into 3 bits of physical address, and I am keeping the 12 bits, which is enough for 4K addressing. Remember, 12 bits are good for 12 bits. 2 to the power 12, okay, is good for 4K addresses. So this is my address within the page frame, also my virtual page. The important thing here is that by looking at this lookup, I do this translation from the virtual addresses to the physical addresses. And remember, we didn't have all the pages available, these access, and in my page table, okay, in my page table, I show them as zeros. We say that, okay, this page is not available, it is not in the memory, this is not in the memory, these are the zero. So this is these are called available bits. Okay, so this translation has to be done every time I make a memory reference. Sounds expensive because I do lots of memory references, but this is done in the memory management unit, and these are very fast memory locations. In fact, sometimes these are registers, okay, L1 cache stuff, and these are done in a very, very efficient and fast way. Remember what I said? We get lots of help from the hardware. Hardware is helping us to make this translation from the virtual address space to the physical address space. Hardware knows about this. Question: where is this table kept? It's a large table. Where do you keep this table? If I go,
in the
somebody said something, but I did not understand.
main memory.
If I keep that table in the main memory, okay, anybody has ideas? What would be the problem if I keep this table in the main memory? If I keep this table in the main memory, there is a serious problem. What is the problem?
It will be edited.
Yusuf, I did not understand what you said.
The process may try to write the table, something that didn't get right.
Well, if you are talking about the protection. Well, I keep it in the kernel space maybe, but there is a much more serious problem than that.
Speed might be a problem.
Speed is the main problem. I mean, if I keep this in the main memory, every time I make a virtual memory reference, that means what? I need to go to main memory and make a search on this table, an array, make a multiplication and find the corresponding bit values and make this change and etc. So remember our, where is, yeah, okay. So every time I make an instruction execution, okay, I like to do this in nanoseconds. But if I am going to go to main memory every time to make this memory reference, it is 100 nanoseconds. It is too slow. So you are making your computer almost 100 times slower. Nobody is going to accept it. Okay? This table has to be where? Look at this picture now.
MMU.
It has to be in the MMU, definitely. It has to be in the MMU. Okay, this table is going to be in the MMU. And MMU, it has to be, and those elements of that array has to be very fast. In fact, they have to be like registers, okay, as fast as registers, so that every time I make a memory reference, I don't spend that much time to get the physical address from the virtual address. Okay, but as always, things are not that simple, and we are going to see that we will have to find a solution because that table is going to be very large. I mean, in this case, it is just 16 registers, and we can afford it. but it's going to be much larger than 16 for today's computers especially. Another question. This page table, this is called the virtual page table. How many page tables are there in my whole system, whole operating system? Is there a global page table, or I have a page table for each process?
I think for each process.
Yeah, we need a page table for each process, right? Because every process has its own virtual address space. And since they have their own virtual address space, who handles the virtual address spaces? These page tables, right? So I need to keep this page table somewhere in my maybe process table, right? So whenever I switch from one process to another process, I need to load this page table from the process table. So context switching became more expensive. Why? Every time I do the context switch between two processes, I have to update my page table too. I have to update my page table too. Since page table is in the MMU, I need to update it. And that's going to be very expensive. That's going to be expensive. So our context switching is becoming more and more expensive. I mean, more help you get from the hardware, more tricks you use like this, like the page tables and etc. Well, in that case, every time make a context switch, you need to load all of this data from somewhere in your memory, and that's going to make your context switch even more inefficient. Okay, good. I think you understand the idea of virtual memory and paging. Let's go back to the original claim. We said that this will eliminate all the allocation inefficiency. So can somebody tell me how did we eliminate this allocation inefficiency? What was allocation inefficiency? Allocation inefficiency was like I need to find the place for my process. If I use first fit, best fit, worst fit, etc., sometimes I may end up not using 1/3 of my memory, right? That was allocation inefficiency. So how did I handle this allocation inefficiency? We say that we don't have allocation inefficiency anymore.
For example, there is no external the fragmentation. What was the name? I forgot that.
Yeah, external fragmentation. You cannot have an external fragmentation. Why? Because if your process needs here, if your process needs, okay, 64 kilobytes of data like this one, like virtual space, okay, well, there is no space like that in my main memory anyway, okay, so I am not going to allocate 64 kilobytes of physical memory. I am going to allocate at most 32 kilobytes of physical memory. That's one thing. The other thing is that I don't have to contiguously allocate any memory. So I don't have to search for spaces. If this page is available, then allocate it. If this page is available, then allocate it, and I will change my page table accordingly. So I don't have that allocation inefficiency problem anymore, right? Allocation efficiency problem anymore. Compaction, again, since I don't have an external fragmentation, there is no compaction. I don't have to relocate anything because there is no contiguous allocation. How about this memory protection? What does that mean, memory protection? It helps us solve memory protection. Maybe for this one I will wait a little bit more, because when I show you the real elements in a page table, you will understand. Okay, this page table is very simple. Okay, this is not realistically simple. Okay, this is very simple. We have more information in our page table than that. Okay, So in your page table, definitely you need to have the physical page frame address. Also, you need to have the available bit. There are many other things like the protection bits. Can I read that page or write to that page, execute it, etc. Okay, that kind of stuff, and you will understand what we mean by that. Okay, and this is how the main algorithm is done. We divide the virtual address into V and O. V is the virtual page number, O is the offset. So here, this is my virtual address. I divided this into V and O. V is the virtual page number and O is the offset inside the virtual page number. Okay, O addresses inside my page frame, and O is always 12 bits for my system, and V is always 4 bits. Since it is 4 bits, okay, there are 2 to the power 4 virtual pages. Okay, there are 2 to the power virtual pages. Since O is 12 bits, that means that my pages are 2 to the power 12, 4 kilobytes. Okay, there are 16 virtual pages and there are 4 kilobytes of data in each page, virtual page or physical page, doesn't matter. Okay, so I divided my virtual page into two, V and O. Okay, V is the virtual page number, O is the offset. And then the memory management unit, MMU, maps V into P. Okay, it takes V, it makes a lookup in this array. Making this lookup is not that difficult, and it produces this P. Okay, P comes from this table. Okay, it is here, 110 P. So I got this P. P is red. Okay, V is green, and I produce this P or address, which is the physical address that I am going to use in addressing the physical memory. In its simplest form, okay, this mapping is done by direct indexing into an MMU register bank. There is a register bank in the MMU. You put V, okay, into this array, and you get a value P out of it, and this would be your physical address. Okay, and you might say that this is similar to base and limit registers that we had looked at last week, but this is faster than that. Why? Because with the base and limit registers you had the addition. Addition is not that fast because it needs the carry. Okay, carry bit. Remember the carry bit? No, this is not like that. Okay, this is simply a lookup. You get a value from this table, and you just put these together to make a new address. So there is no addition. There is no addition. This red part and the blue part doesn't have to interact with each other other than making this concatenation. So I replaced these 4 bits with these 3 bits. That's what I did. So this one has total of 12. This one has total of 16 bits virtual address space. This one has 15 bits physical address space. So their sizes are different. Okay, good. Any questions? Any questions? Let's look at the more realistic structure of the page tables. Okay, in this case each page table has 2 elements, the page frame number and the available bit. It is more complicated than that. Okay, so it is the page frame number. I have it. Okay, I have it here, and present absent bit, like that 10. So this part we already have seen. Okay, so how many bits are there in the page frame number part? How many bits are there in the page frame number? Okay, if my main memory is 2 to the power 30, how much is it? 2 to the power 30 is kilobyte, megabyte, and gigabyte. Okay, so it is 1 gigabyte of data. If my main memory is 1 gigabytes, and if my page frame sizes are 2 to the power 12, 4 kilobytes, how many bits do I have in the page frame number?
About 8 bits, maybe.
8 bits? Where did you get that idea, 8 bits?
I don't really know.
No, the answer is not 8. So let's go back to this figure now. So
18 maybe.
yeah, it is 18. Yes, exactly. It is 18. Why? Because this is my physical memory. Okay, my physical memory is 2 to the power 30. Okay, 2 to the power 30, and each of my frames are 2 to the power 12. Okay, so how many page frames do I need in my physical physical hard disk space? Of course, it is 2 to the power 30 over 2 to the power 12, which is 2 to the power 18, which is around how many is this? 2 to the power 18 is 256 kilo elements, right? So my page so there are 256, or more than 256,000 page frames, and for each page frame I need an element in my page table. So my page table will be of size 256 kilo elements. So that's a very large page table. That's not going to fit into my MMU, but we will solve that problem later. Okay, anyway, so try to do these kind of calculations yourself. So this is the page frame number. So this page frame number, the number of bits depends on your page size, also your main memory, physical memory size. And then I have my protection bits. For example, for that page, am I allowed to read it, write it, execute it? There could be some pages where it is only read only, right? There could be some pages where I can write or not write. And there are some pages which are execution only. You don't write to them, it is just for execution. Okay? So it's called the protection. And then I have this modified bit and the reference bit. What is modified bit? Modified bit says that, let me put it in here. Let me put it in here. Let's say I have, oh, come on. Sorry, I don't have the ability to draw a straight line. Let me try it again. This is as straight as I can do. Okay, So this is the modified bit and bit. Let's say this is modified, this is not modified, modified, not modified, 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 like that. Why do I have a bit for the modified for each page? Why do I have a modified for each page?
Is it run other processes if they are trying to read something from this process?
Mohammed, can you start from the beginning?
I said, is it to run other processes if they are trying to access or read from this particular process? Like, if they are trying to access some data in this process, if they are modified, we warn them that the data is modified.
Well, your voice is coming a little bit interrupted a little bit, but as far as I understand, you said that if some other process is modified and etc. No, well, we don't talk about the other process. Maybe you didn't say that, but the idea is if I had modified this page in the physical memory, okay, if I had modified this page in the physical memory, if I don't need this page anymore in my physical memory, I need to write it back to the disk because I modified it. If I did not modify it, then I don't have to write it back. So swapping will be cheaper. Okay. So modified pages are usually called dirty pages. They are dirty and they have to be written back to the disk. That's the modified bit. Otherwise, when I swap pages, I always have to write them back to the disk, even though I did not change anything in that page. Okay, so modified page, and there is a reference bit. Reference bit is that nobody has referenced this page at all, or it was referenced. If nobody has referenced this so far, that means that it can be replaced, right? If nobody's referenced it, and there is this caching disabled, that means that I don't want this page to be cached. Sometimes I don't need those pages to be cached, and we are going to talk about it later. Okay, good. You understand the meaning of the page tables? Okay, this is a page table. It is inside the MMU, and MMU is responsible from converting the virtual addresses into physical addresses, and the process of converting this virtual address into physical address is done this way. It needs a table lookup, an array, and this table is kept inside the MMU, and this is done in a very, very fast way. But the thing is this is a very simple computer, just 64 kilobytes of virtual address space and 32 kilobytes of physical addresses. Nowadays we don't have those, like the computers like those. Okay, our memories are like 2 to the power 30 1 gigabyte, or 2 to the power 32 4 gigabytes of main memory, and our page sizes are still 4 kilobytes. Okay, so that means that with 4 kilobytes of page sizes and 32 to the power 32 main memory, that means that there are 2 to the 20 pages available. So our page table is going to be 2 to the 20 as a mega element, right? There are 1 mega elements of page tables, and that's not going to fit into our MMU. MMU is not that large. Okay, it has to be small. Since it is small, it is fast. If you make your MMU as large as 1 megabyte, and if you need that information for each process differently, that's going to be difficult. So what am I going to do? I cannot keep my page table in my main memory. That would be too slow. So I need to find a solution. Can anybody help me in this case? I need this to be in the main memory, but I need this to be in the MMU. But for MMU, keeping this kind of 1 mega elements of, okay, each, let's say each each table entry is, let's say, 8 bytes. So 8 megabytes of data. I cannot keep 8 megabytes of data in my MMU, but I like to keep it in my MMU so that it is fast. Otherwise, this virtual address thing cannot be usable. It is 100 times slower than the alternatives. So what am I going to do? I cannot keep it in my MMU. For MMU, it is too large. I cannot keep it in my main memory. Main memory is too slow. What would you do?
Add another virtual memory layer.
Say it again, Yusuf.
We can add another virtual memory layer.
Just explain that a little bit.
We have two virtual memory table, one for the MMU to our disk, another table to this the real address.
Yeah, that's a nice idea. And you are saying that I would keep the first one, small that can fit into MMU. And if I cannot find whatever I need in MMU, that's a second MMU fault, whatever you call it, Yusuf fault. Then I will have to, in that case, I will have to load it from the disk. Yeah, the idea is kind of the same. Yeah, that's so. Maybe we shouldn't call it a second page table. Maybe we can call it a cache. Okay, cache. We are going to use a cache solution for this, and it is called translation look-aside buffer. Translation look-aside buffer is like a cache. It is small and fast, and it keeps some part of the page table in the MMU, but not all of it. Okay, not all of it. And whenever I need to translate a virtual address into a physical address, I look up this translation look-aside buffer. If my page is there, then I am done. Otherwise, I need to load that data from the main memory, not from the disk, from the main memory. So it's like exactly like a cache, and it works most of the time because why do the caches work? Because locality of reference, right? Remember the locality of reference. Whenever you run a program, you don't access your memories in a random way. Usually your access is localized, sequentially. Okay? So locality of reference is there, and we are going to use locality of reference to make this TLB more efficient. Okay? And we call this translation look-aside buffer. Okay, so that's good idea, Yusuf. So you invented translation look-aside buffer, but you called it something different. Any questions so far? Any questions so far? I have a question. If this is the solution, if this is the practical solution for all the problems that we had before, okay, like the compaction problem, swapping problem, external fragmentation problem, why did I talk about those algorithms if nobody is using them? Why did I spend like 2 hours of yours to talk about best fit, next fit, worst fit, quick fit, and talk about these kind of free nodes and etc. and etc.? Why did I talk about them? Why did I talk about base and limit registers?
Maybe these are essentials, legacy essentials. We need to know them.
Because people have used these ideas before the virtual memory. Okay, If I introduce the virtual memory directly, you would not understand why we are using it. But when you compare them with what people had used before, like the swapping, and of course swapping is already there too, but like the overlays and base and limit registers and dynamic allocation, static allocation, etc. So in order to show you why we have this nice solution, compact solution, we introduced this, and this one was introduced, and this virtual memory is introduced in 1960s again, like everything else, and we keep still using it. We still keep using it. It has lots of advantages. Of course, we need very serious amount of hardware help in the form of MMU. Okay, good. Okay, that's it for today. Tomorrow we will continue from this point, and we will talk more about how we keep such large tables in our MMU and main memory. Okay, I'll see you.
Last week you said we were going to talk about midterm
Yeah.
time.
So let's do our midterm next week. Is it okay?
Next week, which day?
Monday or Tuesday. On Monday is okay. Next week let's do it on Monday. So your midterm will be, let me look it up from here, 26th of April 26th 2021 at class time at 10:30. It's going to be a 2 hour exam, written exam. I will ask you 3, 4, 5 questions, and you are going to use your camera to record yourselves, and you are going to submit your answers. Okay, so April 26th. So I was supposed to do the midterm this week, right? So we are delaying it 1 week. Okay, next week, April 26th. It is not a holiday or anything, right? Like, yeah, okay, no problem. So we are going to do it on April 26th at 10:30.
May I add something?
Sure.
Can we have an option to some of us to attend it in school?
You like to do it in school?
Yes, because the disadvantages of this online stuff.
So you are not going to be recorded. You are going to. I don't know. I don't think that the university will let me do that, because you know the epidemic, right? It is not going very good. If people hear about it, that I am doing face-to-face exams, I don't think that I can.
Okay.
So you have connection problems?
This is so stressful to be
No, I mean, I did this for 2 or 3 exams, and some people had connection problems, some people couldn't submit their answers, but nobody failed any of my courses because of those kind of problems. Okay, we always found a solution.
Okay, thank you.
So don't be scared about what if my connection is broken, what if I cannot submit, what if this and this happens, and etc. I mean, if that happens, if many things go wrong, you have a connection problem, electricity is gone, you cannot connect to anything, and etc. I will give you a makeup exam. I will do maybe a face-to-face exam just for you in this university, because that happened, etc. Okay.
Okay.
So don't be stressed about those kind of problems, but be stressed about this course. Okay. This is not an easy course. You need to know lots of stuff, and questions will be accordingly. Study hard, but don't think too much about. Of course, be prepared, but don't be stressed about connection problems and submission problems and etc.
When someone watches you indirectly and doubts you about if you will if you will do something bad and etc. It will uh, it feels uncomfortable, uncomfortable. That's that's why I asked you about this.
Well, as I said, no, I mean, this course is tough, I know. There are many people fails this course. Half of them failed last time, but none of them failed because they could not submit their answers or there was a connection problem or technical problems. Okay, if you are going to be stressed about something, be stressed about the material that we have covered.
Okay, thanks.
Okay, good. Okay, see you tomorrow morning.